Okay, good afternoon, everyone. Let's get started. So, first of all, we just give you a reminder that if you haven't studied your preparing your midterm project report or haven't started doing your project, please start. We have some kind of expectation on your midterm project report, right? And also, please leverage the office hours. Right? And let us continue with the probabilistic graphic models. So in the last lecture, we talked about how do we construct a Bayesian network, right? Which is a type of directed graphic model, right? And given Bayesian network, we're interested in detecting the possible conditional independence between the variables in the graph. Right? To do that, we introduced three basic cases, right? So the first case is called tail-to-tail. Right? As the name suggested, if you got three random variables or nodes in your Bayesian network, A and B and C is always in the middle. If the arrows meet in the intermediate node C with both heads, which is with both tails, which is called tail-to-tail, right? Tail-to-tail. And that was called tail-to-tail case. And from the graph, we can conclude that if condition of nothing A and B are dependent. However, if a condition on C, meaning that C is observed, condition on C and B are independent. Okay? So we did some kind of analysis and tell why these are true. Okay? And then we went through the second case, which is called head-to-tail. Okay? So in the intermediate node C, if the two arrows meet with the pattern that head-to-tail, one is arrowhead, one is tail. Okay, it's called head-to-tail, and then we have the same conclusion as in the case of tail-to-tail. Right? Namely, A and B are dependent if the condition on nothing. However, if C are observed and are conditioned, then A and B are independent. Right? So we can use pretty similar analysis to show this is true. And third one is a little bit odd, right, as compared with the previous two cases, right, which is called head-to-head. Namely, the intermediate node where the two edges meet are both arrowheads. Right? That's called head-to-head. Right? So in other words, A and B are both parents of C. And in this case, we arrive at an opposite conclusion to the previous two cases. That is, if we condition on nothing, meaning that C is unobserved, then A and B are independent. However, if we condition on C, then A and B are dependent. Okay? So the first case is very easy to show that if you just write down the joint probability here, right? And you marginalize out C, you see that actually the joint probability of A and B is the product of P of A and P of B. Right? Obviously, A and B are independent. Right? And then if you want to look at why the conditional independence does not hold, I ask everyone to do a practice, right? And it's possible to show up as a homework question. Right? But here I just give you a hint. So if you want to show that A and B are independent given C, that basically means that you got this conditional probability of A given B and C equals to the conditional probability of A given C only, right? So it means that condition on B doesn't matter, right? If we condition on B or not, right? So to show that, you have to show that, okay, this guy, if you express it, if you write it out according to Bayes' rule, it will be the joint probability of A, B, and C divided by the joint probability of B and C only, right? And then just leverage the decomposition structure reflected in this head-to-head structure, which is P of A times P of B times the P of C, P of A and B, okay? Divided by, we're going to marginalize out A, right? Right. So of course, you're going to marginalize out A, right? So you have to show that if this conditional probability equals to P of A given C, that means you can simplify this fraction by removing B, right? Because this conditional probability on the right hand side doesn't contain B at all, right? It is only some kind of function containing A and C, right? There's no B here. Then you need to check if, in general, you can simplify this fraction by removing B. And in fact, it's not possible. The reason is when you do this integration, right? When you do this integration, you actually couple A and B. Oh, sorry, your couple B and C. Why? Because in this conditional probability, you're gonna integrate out A, right? So in this integration, you're gonna always couple B and C, and you cannot cancel B out. That's the reason that in general, you won't be able to remove the variable B in this function. So you cannot conclude in general that A and B are conditional independent given C. This is a hint, so please just do some kind of math exercise and to verify this point and deepen your understanding. And then we'll mention that actually this is just one case, right? In general, if you have this head-to-head structure, right, and given this descendant C, right, any descendant of C, meaning that starting from C, you point it to the next variable, and that variable point to the next variable. If any of this descendant of C, say D, is observed, then condition on C or any descendant of C, A and B, are not conditional independent. And you can show this result with the same analysis idea we just discussed. Okay, any questions so far? Okay, so before we wrap up the three basic cases, we just want to showcase some interesting effect in Bayesian network, which is called explain away effect. Right? So a prominent example is based upon this head-to-head architecture. Right? So we're going to create some meaning for the variables in this head-to-head Bayesian neural network, right? Bayesian network. So we define three random variables: B, F, and G. So B and F are parents for G, right? So what does B represent? So consider a scenario or application. You watch the status of your car, right? So you want to look at if your gas tank is empty, and also a fuel tank is empty, so which is abbreviated as F, right? And you also want to know what is the read of your gauge, right? So if you look at the gauge, sometimes the gauge shows empty, doesn't necessarily mean that your fuel tank is really empty, because also relate to the battery in the sensor, right? So there's a sensor installed on your fuel tank, and sensor can detect if really you're running out of your gas, right? So actually there's some kind of variable relationships between the battery status, the fuel tank status, and the gauge rate. Does it make sense? So just use a Bayesian network to model their relationship. Okay. And for simplicity, we assume all these three random variables, battery status, fuel tank status, and gauge rate are binary. So B is 0 just means battery is dead. B is 1 meaning the battery is alive. And fuel tank is 0 means it's empty. 1 means that it's not empty. Okay? And gauge rate is 1 mean that the rate is not 0. And if it is 0 means that okay, it's 0 rate. Right? So this is our model. Right? So assume that okay, our prior belief is that okay, the battery is working properly, meaning that the prior probability of battery is alive is 0.9, and the prior probability the fuel tank is not empty is 0.9 as well. Right? And then given different values of B and F, namely the battery status and fuel tank and status, we have the conditional distribution over the gauge rate, right? So all those settings are reasonable. For example, given battery's life, meaning that your sensor most probably is working properly, right? And given your fuel tank is not empty, then your gauge rate will have large chance to be non-zero, right? So we set it to be 0.8. Right? And it is a small probability event that your fuel tank is empty, the sensor is working normally, right? But you still will read a non-zero gauge, right? I mean, this is not impossible, right? But the chance is really low. Right? However, if your battery is dead, right? The battery is dead, B is 0, it's not alive, and then no matter if your fuel tank is empty or not, right? Condition on that, your gauge rate has a low chance to have a non-zero rate. That's the basic setting of our model. Any question? Okay, so we want to look at, okay, two cases. First, given this model, right? Suppose I observe, case one, suppose I observe my gauge rate is 0, meaning that my gauge rate tells me, okay, I'm running out of my gas. Right? I want to calculate the probability that my fuel tank is really empty. Okay? So by using this model, right, this specified model, we can use Bayes' rule to compute that this posterior probability is 2.257. Right? So you might be a little bit feel a little bit weird why this probability is relatively low, right? The reason is that this probability actually considers the cases where your battery is alive and battery is dead. So imagine that if your battery is working properly, and then your gauge rate is 0, then very probably that conditional gauge rate is 0, then your fuel tank is really empty, right? However, it should also consider the case that your battery is dead. Right? In that case, actually, even your gauge rate is 0, it doesn't necessarily mean your tank will be 0 as well. Right? So you have to synergize all those two cases because right now we don't know if your battery is alive or not. That's how we compute, and this is our result. Right? So this is case one. Right? And case two is that okay, I not only observe my 0 gauge rate, but also observe my battery is dead. So look, now we are conditioned on more information. We know more results. We not only know, okay, the gauge rate is 0, but also know the battery is dead. Then we can compute condition on these two results, right? What is the probability my fuel tank is empty? Again, when I apply the Bayes rule, we find that the conditional probability of empty fuel tank given 0 gauge rate and dead battery now becomes 0.111. So you can see that this probability is much smaller than the last probability we discussed, where you don't know the battery status. Right? So why this probability decreases? I mean, intuitively. Yes, exactly, right? So actually, by additionally conditioning on the battery status, I kind of take some explanation of zero of empty tank status away, right? Because I attribute the possible reason that your gauge rate is zero, partly to the zero battery, the dead battery status, right? And then because I take away this explanation effect, when I compute the conditional probability that your empty tank is empty, it's getting smaller. Right? So this is also reasonable, right? So in practice, well, I don't know some unknown variables. I don't know some status. Well, I might have some like a higher estimation, right? However, if I know a little bit more information, I kind of like attribute this observation due to some known information, right? So I take away some kind of effect, and then my estimation of my computation of that probability can be reduced. So this is so-called explanatory effect, and it's an interesting observation in the Bayesian network model. Any question? Right. So this is this is reasonable, and this is also kind of like supporting other Bayesian network-based system, because early stage of probabilistic learning, people are interested in building expert system. Like for example, if I'm using Bayesian network to build up some diagnosis system, right? There's in MIT, there's an early project. It's called QMRT. It's a very well-known project. It is an expert system built by two-level Bayesian neural network, Bayesian network to predict a type of like, I kind of forgot, it's kind of influenza or something like that, based upon different type of syndromes. Right? Of course, the more syndromes you have some kind of different probability of diagnosis result, right? And that kind of structure also exhibits some explanation, explanatory effect. Like for example, if you have sniffle, right? You have some sniffle, maybe a probability of you're infected by some by the cold is small. However, even if you follow the condition, you have a fever, this probability is high, right? Because fever can explain the diagnosis of the influenza. Same time explain you have sniffle in the nose, right? So these are interesting phenomenon which people observe from Bayesian network. Okay, so now we have finished talking about three basic cases like conditional independence. So now we want to ask a general question. Right? In general, given arbitrary non-intersecting sets of nodes A and B and C, so A and B and C are three sets of nodes, right? And they're non-overlapping. Then how do we test if conditional C, the set of random variables in A are independent to the set of random variables in B? And of course, the number of the variables in A and B and C can be much larger than three nodes, right? So it's much more complicated than the three cases we discussed. So we're gonna introduce the so-called separation or baseball algorithm to efficiently test this if this conclusion is correct or not. Right? How can we do that? So first, because we want to test the condition independence, so we're going to shade all the nodes in C. The graphic model just means the variables in C are observed and conditioned, right? And then we're going to enumerate every path from any node in A and any node in B. Right? So you can basically imagine like, okay, this is quite a few nodes in A, right? This is quite a few nodes in B, and there could be many passes, right? From any node in A to any node in B, right? And C might have some nodes in the middle of those paths, or might not have any nodes in this middle path. It doesn't matter. And then we're going to test every path. For every possible path, right? We just go through every node in this path. We'll look at the arrows meet on this node. If we have seen the pattern that it is head to tail or tail to tail, at the same time, this node is in C, meaning it is shaded. Then we will, this path is blocked, and we're gonna look at another path. Of course, if you don't mean that, you just continue going through this path, right? Look at next node, and if say you have the same head to head and head to tail, and this node it is in C or not, right? Or if you see a node on the path meet head to head, right? And neither the node or any of its descendants is in C. So this is third case, right? Third basic case. Then we will, this path is blocked as well. So it's like you got a path. You got a path. This is a current node you're looking at, right? And if this node is not in C, not in the condition part, and any descendant of this node are not in C as well, then we will, this path is blocked. And then you try to examine the next path. If every path turns out to be blocked due to any of these three cases, okay, then we can conclude A and B are independent conditional C. However, if there is just one path, or at least one path, which is showing to be not blocked, then we claim that this conditional independence does not hold. Does it make sense? Block is like, just like you threw a ball, right? Yeah, you start in some node from A, you go through that path. That means you're gonna go through every node in that path. And if any of these three cases happen, that path has been blocked, and your ball has to be bounced back. Right? So if every path turns out to be blocked, meaning that your small ball cannot go through every path from any node in A to any node in B, then we claim A and B are conditional independent given C. However, if your small ball can go through any path, then the conditional independence doesn't hold. Does it make sense? Okay. So, I mean, emphasize again, right? So, oh, sorry, I shouldn't. Yeah, you can see that there are many paths, right? So imagine that you got a path, you got a small ball, right? Something like that, right? This is a starting point, which is belongs to A, and end point belongs to B, right? You're trying to throw a small ball over this path, right? That means you're gonna try to, starting from here, move to the next node, move to the next node, move to the next node until you arrive at the ending node, right? But however, whenever you look at a new node, right, you want to check if these three cases happen. If any of these three cases happen, that means, okay, here is blocked, right? The ball has to be bounced back and return to the starting point. Right? That means this path is blocked. Then you're gonna check another path, right? And trying to throw your ball and let your ball go through this path. Right? If it turns out every path is blocked, that means there won't be any path that allows you to move your small ball from a node in A to a node in B. That means, okay, there are set A and set B are condition dependent. Does it make sense? Right? If this violates, right, for any path, right, that means you can check out one path which you can smoothly move your ball from a node in A to a node in B. And then that means A and B are conditionally independent, are conditionally dependent. We're on the same page now. Any questions so far? Okay, so now let us use a concrete example, right, to showcase how we run this baseball algorithm, right? So we look at this same Bayesian network, but condition on different set of variables, right? So first, we define our A is just a one node here, right? And our B is node here, right? Our C is here, right? So if you want to check whether A and B conditional dependent on C, right? Given C, right? How can we do that? We just look at every path starting from a node in A, ending a node in B, right? So how many paths do we have? How many paths do we have? Just one, right? Just one. Just here, here, and here, right? So imagine you got a small ball here, right? You're gonna try to make your ball to go through this path. So let us do it one by one, right? Of course, the first node, you can go through that. Now your ball is here. Now, what can we observe? What kind of basic case do we have? It's head-to-head, right? So head-to-head is blocked only when its descendant is not conditioned or is not shaded, right? But here it is shaded. What does it mean? It means that this ball can pass through E, right? Right? And then we move to F, right? So what's the case do we have for F? Okay. It's tail to tail, right? And tail to tail is blocked only when this F is observed, right? Or in C, right? Unfortunately, it's not observed, it's not shaded. So that means it can pass through F as well. Then we arrive at node B. Right? So now we found that actually our small ball can go through its path. What does it mean? It means it is not conditionally independent, right? Does it make sense? Just be careful of the tail to tail case, right? Head to head case, right? So if you look at here, right? If you can go through this node E, depends if E is in C, or any of descendant of E is in C, right? Only when E is not in C and all of its dependents are not in C, this node is blocked. Otherwise it means you can pass through it. That's how our third case tells us, right? And for the other cases like tail to tail or head to tail, it just means the node itself must be conditioned or shaded, right? It means blocked, right? So it's kind of like a little bit contradictory. Just need to pay attention to, right? Any question so far? So now I want to change this problem a little bit. What if I now define my C not only by this node C, but also the node F. So meaning I'm gonna shade this node F. Do we have this? Do we have conditional independence now? Any thought? Again, we just run an algorithm, right? As we said, right? If any path where your ball can go through it, that means the conditional independence does not hold, right? So let's see if our ball by conditional additional variable F, if our ball can go through it, right? So as we mentioned, like if your small ball start from A, you go to E, right? Because E is descendant C is some C is observed. That means okay, you can pass through E, right? But then you arrive at node F, right? The ball is stay here, right? So can your ball go through F? No, right? Because you have a head to tail to tail case. For the tail to tail case, if the node has already been shaded, observed, that means this node has been blocked. Right? Your path is blocked here. That means your ball is not able to pass through this path. Right? And there is only one path between A and B. So that means your ball is not able to go through every path between A and B. So in this case, the condition independence is correct. Right? Both. Does it make sense? And now let us look at the third example where your A is still the small a, your B is still small b, right? And then your C is the single node F. So now I want to ask if big A and big B are condition independent given C. Any thought? Yes or no? Yes, right? So just look at like if your small ball starting from here, you arrive at E. So now I want to ask if E is blocked or not. E is blocked, right? Why? Because E is not observed, or not shaded, and E's descendant C is not observed. So here, that's already being blocked. You're even not able to arrive at F. You have a being blocked at E. Let's just tell that, okay, A and B are independent. Give me C, right? Okay, hopefully these 3 concrete examples can give you a sense how the baseball algorithm is running. And it's actually even simpler if you write some algorithm to do that, right? Just check out every case, right? And see this case are satisfied. If they're satisfied, then this path is blocked. You're gonna just look at another path. Okay. Next, we're going to introduce the concepts called Markov-Blanky. So consider a Bayesian network. And in this network, you have D nodes. You have D nodes, like x1 to xd. And for a particular node xi, we want to ask, right, conditional on what set of variables xi are independent to the remaining variables. So you can view like, okay, here's like xi. And all the other variables, let us denoted by x, not I, right? So we want to partition the remaining variables by two sets, right? One is S, the other is let me do not use this awkward notation. Let me assume, okay, the other set is Q, right? So S and Q are not overlapping, right? And S union Q is X not I. Right? So I want to ask, right? Conditional on what set of random variables S, Xi is independent to Q. So basically means this holds. Okay. And this S is called a Markov-Blanky. Does it make sense? Okay. This is definition. So if you want to look at a particular variable, node xi, right? We want to know conditional on what set of random variables S, xi are independent to all the remaining nodes Q. So called S is kind of Markov-Blanky. You can view it as a kind of like a build up a wall which can separate out at xi and all the other variables outside. Are we on the same page? Right? In the definition, right? So the question is, how do you identify S, right? So we give two ways to identify the Markov-Blanky S. Right? So first, from the algebraic will, right? So if we look at the full conditional probability, right? Xi given the remaining variables other than Xi, so this guy should be S union with Q, right? So according to the definition of Bayes rule, it is the joint probability of x1 to xd divided by the marginal probability, right? Marginalized out xi, right? Here, right? And according to the definition of Bayes rule, well, the joint probability is just the product of a set of conditional probabilities, right? P of each xk given the parent of xk. Of course, some variable do not have any parent, right? So the parent is just empty, right? And then in the denominator, you just marginalize out xi from the product of those conditional probabilities. Right? So if you want to know what is S, so meaning that after compute this the full conditional probability, some variables, namely those variables in Q, must be canceled. Meaning that after some simplification, right? Simplification of this fraction, there will be only xi and the variables in S are preserved. All the other variables are canceled out. And they are Q. Does it make sense? Because according to the conditional independence, right? If given S, xi are independent to Q, that just means the full conditional probability equals to the conditional probability of xi given S only. Right? Does it make sense? Any question? Everyone's good? David. Yes. So we are using this definition. Right? This is definition of conditional dependence. Right? So this guy is actually P of xi. I mean, this whole formula is just the P of xi given S and Q, right? So we're going to do some kind of simplification. We're going to reduce to P of xi given S. So that means all those variables which are canceled out will be those Q that are conditionally independent to xi, right? So now, if you look at the numerator and the denominator, imagine what kind of terms will be canceled out. So this guy and this guy, these two products are exactly the same, right? The difference is that, okay, in the denominator, you're gonna only integrate out xi, right? So we can imagine that if you got some P of xk, pak, both the target variable xk and the parent variable do not contain xi, then they can be moved out of this integration, right? It's like, for example, P of x1 given x2, P of x3 given x4. If you're gonna integrate out x1, P of x3 given x4 are constant to x1, right? So they can be moved out of this integration, right? And P of x3 given x4 also appears in the numerator. So they're gonna be canceled out. Does it make sense? And then our observation will be, okay, if you got any term, like P of x, let me use another term like xj and paj. If xj and paj do not contain xi at all, then this guy will be viewed as constant to xj. In the integration, they can be moved out from the integration. And also, this guy appears in the numerator, they can be canceled out. So then that means all the variables in this conditional probabilities, and this conditional probability will be canceled out, right? It will be inside Q. Does it make sense? So that means for all the conditional probabilities inside this product, right? If whose target variable and conditional part do not contain xi, they're going to be canceled out. And their variables form Q. So the remaining variables inside this fraction will be just the conditional probabilities that contain xi, right? Why they must be stay here? Because you're going to integrate, you're going to integrate xi, right? So those variables cannot disappear, right? They are coupled together. Does it make sense? Like, for example, suppose this is your conditional probability x1, x2 given x1 and x3, sorry, x4 given x3, right? And you're gonna marginalize out x1, right? So it's px2 given x1, px4 given x3, and dx1, right? So you know that P of x4 given x3, this conditional probability doesn't contain x1 at all, right? So they're going to be canceled out. That means x3 and x4 will be inside this cube, right? And the remaining part, the remaining conditional probabilities, which you cannot cancel out, they must contain xi. Here, it will be x1, right? Because you're going to integrating out x1, right? So you have to couple x2. Right? They cannot be canceled out. So those variables inside the conditional probabilities that contain xi form the Markov blanket, namely S. Does it make sense? For example, here will be x2, right? There's only one conditional probability, P of x2 given x1 that contain x1, right? So x2 will stay in this fraction, right? And in general, what kind of conditional probabilities are that will contain xi? Xi can be first, the parent of xi, right? You have some conditional probability of xi given, say, x1, x2, x4. So the parent of xi will be in the Markov blanket, right? Or you got some xj, but conditional xi and other guys, right? So xj is the parent of some variable. Then both the co-parents and the target variable, namely descendant of xi, will be in the Markov blanket as well. Does it make sense? Right. So now we're clear who forms the xi Markov blanket, includes the xi parents, xi children, and the children's co-parents. Right. Xi parents means that some conditional probability where the target variable is xi, but conditional on something, the parents, right? Xi's children means that xi is in the conditional part, right? And target variable is called xi's children, right? And also xi's co-parents, right? Conditional xi and say xj plus 1, right? Xj and xj plus 1 are the co-parents. So all those variables together form the Markov blanket of xi. Why? Because they are all appearing some conditional probability that contains xi. Does it make sense? So if you feel this is a little bit uncomfortable catch up, doesn't matter. You just think about the logic here. So if you write down the full conditional probability, if you want to cancel out those terms, which terms will be canceled? Only those terms that do not contain xi at all will be canceled out. And the remaining terms left, I mean, it cannot be canceled out, must be inside the conditional probability that contain xi. And following this thought, you will get why xi's Markov blanket will contain such kind of those kind of variables. Okay. But you can also take a look from the graphing model point of view. Right? So if you write out, if you look at the Bayesian network structure, right? This is a particular xi. If you take xi's children, right? Xi's parents and co-parents, and imagine that for all the other variables, right? For all the other variables, the way they're going to connect to xi always have some structure like head to tail or tail to tail, right? So then if you condition on that, it will always be blocked, right? If you run a baseball algorithm, you find that, okay, all the paths will be blocked and they are conditionally dependent. So perhaps looking at network structure is even more straightforward way to understand why Markov blanket is like this. Any questions so far? Okay. So now we have finished the introduction of the directly graphing model, which is called Bayes network. We found that although this separation is simple, but it's a bit subtle to test the conditional independence, right? You have to look at several basic cases, and also you should really pay attention to the direction of the arrows, right? Head to head, tail to head, tail to tail, right? Head to tail, tail to tail, right? So a natural question will be like, can we construct an even easier graphic model where we do not need to pay attention to the directions? Then it leads us to a second type of graphic model. It's called undirected graphic model, or in other words, it's called a Markov random fields. So in the Markov random fields, if you want to test conditional independence, things becomes much easier. You just look at, again, you just look at all the paths from any node in A to any node in B, and you shade all the paths, you shade all the nodes on the condition set, right? If every path you can observe at least one node shaded, then that path is blocked. You don't need to pay attention if it's tail to tail, head to tail, or head to head, right? And if all the paths are blocked by the shaded nodes, then the condition independence are correct. So it seems a lot easier than the Bayesian network, right? Any question? So we're on the same page, right? So next we're going to talk about how do we build up an undirected graphical representation of probabilistic models. Right? So again, given such a graph, right, we need to define the associated probability distribution over the nodes. Right? So if we have an undirected graphic representation, right, if we want to create a probabilistic model over that, we need to define the so-called potential function on the cliques or maximum cliques. So what does clique mean? A clique means just a set of nodes who are mutually connected. Like for this node, right? This node and this node, two nodes, they're connecting with each other. So they're called clique. But clique is not necessary to be the largest. If you have some set of nodes which are if you have a clique and you cannot add one more node to form a new clique, then this clique called maximum clique. For example, for x2, x3, and x4 here, so notice that they are pairwisely connected, right? But if you add one more node, just one more node into this clique, it is no longer a clique. See, you add one more node x1 here. X1 does not connect to x4, so it's not clique anymore. Then we call x2, x3, and x2, x3, and x4 a maximum clique. So undirected graphic model demand we define a potential function over each maximum clique. And then your joint distribution over all the nodes on the undirected graphic model is the product of the potential function over every maximum clique and then properly normalized. So here we can see this is a product, right? So C here is a maximum clique C. So we're gonna enumerate every maximum clique in this graph, and for each clique, you define a function, and this non-negative function, of course. So we call this function a potential function, which is multiply all the potential functions and then do the normalization to make it a valid probability distribution. So this is how we define a undirected graphing model. Any questions so far? In statistical physics, there's also associated physics meaning for this potential function. Right? The potential function, people usually choose this form. So namely, I can first define a energy over the nodes in a clique. And then I take the exponential of negative energy as my potential function. And then I multiply all the potential functions together, do the normalization, I get distribution. For example, if we want to model a set of molecules, right? You know, the temperature is some kind of united view or single view of the activity of those molecules, right? So how do we model that? So we can define the potential, we can define energy function over every groups of molecules, right? Which can represent how much energy they have. Then based upon that, we take exponential, the negative of the energy function, we define potential function, and multiply them together, we give a distribution over this molecules. That's how the statistical physics they study the activity of molecules. So here's one example of undirected graphing model, which is called image denoising. Okay? So suppose this is our ground truth picture, right? And unfortunately, it was crafted by some noises. So this is a binary image, right? So you got two possible pixel values, right? Yellow or blue, right? But if your image has been crafted by many random blue pixels, right? How can we denoise them, right? So we can build up a undirected graphing model, right? We view each pixel, the value as a random variable, right? So we know that xi corresponds to one particular pixel I. It could be 0 or 1, right? And xi indicates a ground truth pixel value, and yi is the observed pixel value. Okay. And because this pixel, okay, they are put in a grid, right? So we can connect the neighboring pixels to form a graph structure. So that forms our graphing model. Okay. Then, how do we build up a joint probability of the latent ground truth pixel value and observed noisy pixel values, denoted by xi's and yi's respectively? According to the graph structure, we're going to define the potential function, right? So we got there two types of maximum cliques. One is connections or edges between neighboring pixel xi's, right? And the other is between each pixel, between each ground truth pixel value and noise observation, right? So two types of edges. So we're gonna define two potential functions, right? One is here, the other is here. Sorry, I put them out, right? So these potential functions are really simple, right? So for this type of potential function, define the edges connecting to ground truth pixel values. We just multiply xi and xj, and then multiply with coefficient beta, right? And for second type, we just multiply xi and ground and observation, not noise observation yi, and with some kind of parameter eta plus some scale h time multiplying with xi itself. So then we form our joint probability over all xi's and yi's. And then we can estimate, right? Because we got observation y, right? So we want to maximize the posterior distribution of X, namely the ground truth pixel values, given the noisy observations Y. And of course, we want to estimate the model parameters eta, beta, and H here. Right? There are many ways of doing that. I'm not gonna talk about how to do that. But after some kind of like iterative estimation or inference algorithm, this is our restored image, namely the estimation of XI's values. So although it's not like 100% denoising without perfect denoising, we have already seen that many noises have already been removed. Right? David. Potential function, there's not too much restriction. You just need to ensure the potential function must be non-negative, and it's it is bounded. You can integrate out, right? It won't be like if you integrate out X, it give you infinity, and that won't give you a valid probability density. Yeah, that's a very good question. Actually, choice is up to you. Right? You define a structure, right? You define a graphic model in this way, right? But someone say, okay, this might be too simple. I just considering my xi, my pixel, and my neighboring pixel have some direct structure with me, right? So why not I consider some higher order structure like next pixel, and the pixel after next pixel should also connect with me. Of course, you can define that. You can define your own potential function of that to capture more correlations between those pixel values. You can do that. But the problem is that if you do this, you have some more computational cost. So in practice, you always need to some trade off the model expressiveness to the computational efficiency. Other question? Okay. So I know there's an interesting question, right? So suppose I have already had a Bayesian network, right? How do I convert it into an undirected graphic model? Okay. So first, let us use a chain graphic model, chain Bayesian network as an example, right? So suppose my x1, x2 to x big N are in the network is a chain, right? So that means I can write down my joint probability in this way: P of x1, P of x2 given x1, P of x3 given x2 until P of x big N given x big N minus 1, right? So if you want to convert for undirect graph, so first of all, we're gonna remove the arrow in those edges, right? And secondly, we should look at the conditional probabilities, right? So each conditional probability in the Bayesian network actually couple a set of random variables, right? And because each conditional probability is kind of atomic, right? You cannot further decompose it. Right? So like we know that P of x2 given x1, which is reflected from the Bayesian network, we know that okay, P of x2 given x1 is atomic. You don't have any further split of that, right? So that means this guy must be formed in a potential function, right? So then you should construct a potential function that subsume every different conditional probability, right? And the related probabilities. For example, here we know that P of x2 given x1, they couple x1, x2. That means x1, x2 must be a potential function, right? At the same time, we know that x1, the marginal probability of x1 is also here. So you should subsume P of x1 as well. So that's where you define the first potential function, x1, x2. Okay. And similarly, you got P of x3 given x2. which couple x2 and 3. So we have the second potential function, psi to 3 or x2 and 3, which kind of define on this clique, right? So the first one, psi 1, 2 is defined on this clique and so on. So you can see that actually it's pretty straightforward to map the conditional probabilities to the potential functions, right? In this chain network. So next, let us move to a more general case, right? So suppose it's not chain network, right? It is more complex. Say, I got a conditional probability of Px for conditional 3 variables, x1, x2, and 3, right? How do we convert it into undirected graphic model? Again, because the conditional probability is atomic, meaning that all the variables in this conditional probability term are coupled together, right? They must be inside one potential function, and the potential function is defined on maximum clique. So that means I should ensure that in my undirected graphic model, these 4 variables are fully connected, right? They're pairwisely connected to each other. So that means when we convert it to an undirected graphic model, we should, in addition to removing the arrows, the heads of the arrows, right? You should also add in a connection between their parents. So this is called a moralization or marrying parents. Only doing so, you can ensure that, okay, all those variables inside this conditional probability term are fully connected. Right? Any questions so far? So then how do you convert an arbitrary Bayesian network to an undirected graphic model, right? Just 2 steps. First, doing the moralization, meaning for every conditional probability, you just pairwisely connect their parents and then remove the directionality of the arrows. That's it. Someone may ask, are the directed graphic models, Bayesian networks, are equivalent to undirected graphic models? The answer is unfortunately no. Okay. So you can see 2 cases, right? So first case, this head-to-head case, right? A and B and C is our Bayesian network, right? If we want to convert it into a undirected graphic model, what shall we do? So first, moralization, right? C has 2 parents, right? So we're gonna connect them, right? And then we remove the directionality, right? So this is my converted undirected graphic model, right? However, after doing this conversion, we actually lose some property. Right? So from the original Bayesian network, we know that conditional nothing A and B are independent, right? Conditional C and B are dependent. But after the conversion, do we have the same conclusion? Can we say A and B are independent to each other? No, right? Why? Because A and B have already been connected, right? It is connected, and that means that there's a path connecting them, right? They're not blocked because there's not any shaded nodes between them, right? So we are dependent. This has already break this lose this property, right? So you can see that after you do this normalization and directionality removing, you possibly can lose some properties in Bayesian network. On the other hand, if you want to look at some undirected graphing model, if we look at this graphing model, A, B, and C, and D, we can get 3 results. First, A and B are independent. Second, conditional, A and B are dependent, and conditional C and D, A and B are independent, and conditional A and B, C and D are independent, right? You cannot create any Bayesian network which have all 3 results satisfied. You can try that. So basically means that there is some kind of undirected graphing model that cannot be represented by Bayesian networks. So here, we just want to use these concrete examples to show that although we can convert some directed graphing model to undirected graphing model, they are not totally equivalent. Right? In some cases, the conversion can make you lose some properties. In some cases, you cannot find out exact counterpart in directed graphing model. Does it make sense? Okay, so then we have finished the introduction of the basic definition of the graphing model, right? So we would like you to know how to construct Bayesian networks and Markov random field, right? How to convert a Bayesian neural network to a Markov random field, normalization, remove the directionality, right? And be careful, Bayesian network must be a cyclic directed graph. Right? What's the definition of conditional independence? What's the 3 basic cases? Right? Head to tail, tail to tail, head to head. Right? Be aware that there is a explanatory effect in Bayesian network, right? And deseparation. And also be aware that these 2 types of graphing models are not equivalent to each other. Not totally equivalent to each other. Any questions so far? Okay. So now that we have introduced the general framework for model, right? So you see that using graphic representation, it is convenience and it's also flexible for us to represent all kinds of probabilistic models, right? Then we move to the next question, right? How can we do the computation? Right? We're not just want to have some fancy view of our probabilistic model. We also do some efficient computation. That's our ultimate goal, right? So how do we formalize our task in computation? Right? One sentence. Given a graphical model, no matter if it's a Bayesian network or Markov random field, our goal is to compute the posterior of one or more subsets of nodes given observed nodes. That's always our goal. Right? For example, right? Suppose you have this simple graphic model X. We represent some unknown other parameters, right? And Y is observed output some data, right? So suppose we have collected some data. That means Y is observed and shaded here, right? Then our goal becomes, given Y, how do we compute the posterior distribution of unknown variables X? Right? Of course, in the general case, your graphic model can be quite large, right? Many variables, they're connecting in all kinds of complex ways, right? You have collected some data. That means you observe a subset of nodes in a graph, right? Then you want to estimate the distribution, posterior distribution of these unobserved nodes, conditional Just observe those. That's in general our task. So any question for the setting of this task? So on the exercise, our goal is to compute a marginal of one or subset of nodes. So this computation, if we do not use some kind of trick or idea, smart idea, usually is very difficult to compute. How do we see this? Again, we're going to use a chain to explain chain graphic model to explain this problem. Right? So suppose I have n random variables, a chain graph. So here we just remove the directionality, right? To talk about the general case, right? So my joint probability according to the graphic structure is defined as follows, because the maximum click, each maximum click is just an edge which connecting two nodes, right? Successive nodes. So we define a potential function over x1, x2, x2, x3 until xn minus 1, xn. So the potential function will be psi1, 2, x1, x2, psi2, 3, x2, x3, and psi n minus 1, n, xn minus 1, xn minus 1, xn, right? And of course, we have a normalizer z, right? This is what is our the structure of our joint probability according to the chain graphic model. Right. So, and here we assume those random variables are discrete. Right? So each variable can take k possible values. Right? So it can take k possible values. So that means each potential function can take a k by k values. Right? So x1 from 1 to k, x2 from 1 to k, and you different value of x1, x2 give you different potential function value. So you can basically view the potential is a k by k table, right? Is everyone good with this setting? And then if we want to compute the marginal distribution for a particular node xn, right? If we naively do the marginalization, what is the cost? What does it mean for naively do the marginalization? We just apply the summation over all the variables other than xn and adds up the joint probability of xn. What's the complexity? Say for xn equals to 1, you have to enumerate all the other possible configurations from x2, from x1 to x n minus 1 and xn plus 1 to x bigger, right? So each remaining variable has k possible values. So how many possible values in total of their combination? K to the power of n minus 1, right? So you have big N variables, right? If you take a particular value of x small n, right? See 1, and you have to enumerate all combinations of all the other variables values, right? So each variable value can take k possible values. You have n minus 1, big N minus 1 remaining variables. So you got k to the power of big N minus 1 possible combinations values, right? You should evaluate the joint probability for each of this particular configuration, add them together. So you're going to take the complexity of k to the power of n minus 1, right? And this is just for calculating one marginal probability where xn takes 1, right? And you have to take the marginal probability of xn equals 2, 3 onto big K, right? You have to compute this procedure for k times. So then what is the total complexity? Any thought? So each particular value of xn, if you want to count the marginal probability, it will take the complexity of k to the power of big N minus 1, right? You do this k times. What's the total complexity? K times k to the power of N minus 1, right? So actually, this guy, right? Actually, it gives you k to the power of big N, right? So you can see that even for this simple chain graphic model, right? If you calculate marginal distribution naively, the complexity is exponential to the number of nodes in this graphic model. Obviously, this is totally unacceptable. Okay, let's stop here today. On Thursday, we're going to talk about how do we leverage the distributive law to efficiently compute this.